Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, I want to go over something that reminds me of my youth. Well, yeah, that was in the last millennium. I know I'm ancient, but the funny thing is that I had a beloved uncle, God bless his soul, he passed away. Um, he loved math, and maybe I got that from him. I don't know, or my dad. Both of them were like math wizards. I'm nowhere near what they were. And this uncle, he lived in America for a while and then returned to Egypt. So I was very close to him, and pretty much every week he would call me and tell me, "Come on, Mohammed, I'm gonna give you a problem, and you have 1 year to solve." Yeah. So some math riddle. And it would keep me up all night solving it. And then I call him and wake him up and say, "Oh, I found the answer." Until one day, I will never forget it. We didn't have calculators, remember? And he told me, "Can you add numbers from 1 to n?" I said, "Yeah, that's child play." He said, "Okay, good. What? Do you know how to add square numbers like 1 square plus 2 square plus 3 square up to any number, any n, or any number, like the first 10, for example?" I say, "Yeah, I can do that." "How about 1 cubed, 2 cubed, 3 cubed?" I said, "I think also I can do that." He said, "Okay, now can you find a general way, no matter what n is, that if I substitute in it, I get the sum of, say, 1 to the 52nd plus 2 to the 52nd plus 3 to the 52nd?" I'm embarrassed to say, I kept working on this problem for months. Every time I have it, free time, it will like nag me to go and try to do it. And I had to solve, say, 5 equations in 5 unknowns, and then 6 in 6. And then when my mom came to the rescue and got me a calculator, this calculator was, at the time, it was a Texas Instrument, but not a TI. The series there were SR. And I remember it was an SR50 with a red screen, and comes with magnetic tapes and libraries. And I had to install a library for math, and that calculator, don't laugh, at the time it was top of the line. Nobody believed that it could invert a 9 by 9 matrix. However, I have to say, I have to connect it to an outlet, because the battery wouldn't survive until it finishes doing that. And it takes the calculator 12 minutes, believe it or not, 12 minutes working to invert a 9 by 9 matrix, but that's it. So I had a limit. I couldn't go any further. And I will show you what happens. We went over, how to add one, like x to the first, or like n terms, like 1 plus 2 plus 3, or square, or cube. And I said we use those for, finding integrations. If you saw this session. So I know that if I say, if n equals 1, meaning 1 to the first plus 2 to the first, in fact, then I get the sum would be n times n plus 1 over 2. But I'm going to write it slightly different. I'm going to write it n square over 2 plus n over 2. And I'm going to call that S1. Now, if I have S2, meaning I want to add 1 square plus 2 square plus 3 square, and you give me n, I want the first 5 squares. Okay, 1 square up until 5 square. What is that sum? So we know we are going to write it, and then I will tell you how it works. Okay, plus n square over 2 plus n over 6. Okay, so next, S3, Some people will tell you take these and square them. That's correct, but I prefer to write them as that because now you will see the pattern. And I'm going to stop here. You see that the first term, it's as if you are integrating n dn, right? N becomes n squared over 2. N squared becomes n cubed over 3. N cubed becomes n to the 4 over 4, and so on. And so if you want to tell me the sum of 1 to the 20th plus 2 to the 20th plus, I say, okay, n to the 21st over 21. I know the first term, no big deal. The second term only doesn't take 5 seconds because you notice it's always divided by 2. This same power, so you see the power drops by 1, but the second term is always divided by 2. So if I'm adding again 1 to the 20th plus 2 to the 20th plus, the second term would be n to the 20th over 2. How about the third? And why do we have 3 here? It turns out that you see the power increases, of course. Once you get the lowest term is n squared, you start getting a new term. You would say, but I don't have it here. Yeah, the first one is an anomaly, so we'll leave that for it. But if I know that the first is n over 6, and I am in row 2, to find the next element. So if you tell me n over 6, I would say, okay, so I'm going to multiply it by 3 over 2. S4 would be n to the 5 over 5 plus n to the 4 over 2 plus, and then here, what do? I would say, okay, here I multiplied by 3 over 2 to get that. So what do you think I'm going to multiply by? It's a little tricky, but you will see it. It's really so easy. I'm going to add 1 and 1. So I'm going to say multiply by 4 over 3. So the 4 and the 4 cancel, and you get n cubed over 3. And here is the dilemma. Once the lowest term is a square, in the next line, a new term will appear. And I had no idea where this thing is coming from. Okay. It turns out I could solve this equation. Why? Because if you tell me what is the sum of 1 to the 4th, I say it's 1, right? It's if you take only one term. And if you add these, the sum of these coefficients have to add up to 1. Half and a half is 1. Third and a half is 5/6 plus 1/6 is 1. A quarter and a quarter is half plus half is 1. This is not 1. So if you take a common denominator, you see the common denominator would be 30. Divide by 5 is 6. Divide by 2 is 15. 6 and 15 is 21. Divided by 3 is 10. 21 plus 1 is 31 over 30. So I had to subtract n, not n squared. We jump 1. You will see why later. Over 30. I have the S4. If I want to get to S5, it's so easy. S5 is n to the 6 over 6 plus n to the 5 over 2 plus n to the 4. I'm going to multiply that by 5 over 4. So it would become 5n, and you see things becomes more complicated. The negative here, notice in the column here, when the highest power was 3, I multiplied by 3 over 2, and then I kept adding 1 to the numerator and the denominator. Here, I added this, so I'm coming now to the 5th row. So I'm going to multiply by 5 over 2. So that becomes n cubed. 5 over 30 is 1 over 6 times 2 is 12. So I get over, okay? I'm sorry, this is n squared. Notice, because I found n squared, the next time a new term would come. I would write it without showing you where it came from, like I did it. So I'm not going to add the coefficients. I know it's getting hard, but I'm just going to show you the dilemma I was in. And then later, when I found out who found these and how on earth, yes, there is an equation for it, but for that, at that time, we didn't have internet. I didn't have advanced math. I was just a high schooler. So it was like mind boggling for me. How on earth did they get that? Because we didn't learn like, uh, uh, like as I said, advanced math. Again, I'm going to multiply that by 6 over 5. Notice when you multiply by 6, the 5 and the 5 cancel, and 6 over 12 is a half. So that becomes plus n to the 5th over 2. Then here I'm going to multiply by 6 over 3. So 6 over 12 is 1 half. 1 half divided by 3 is 1/6. So I get minus n cubed over 6. Well, I still can do it without a calculator. Why? Because a half and half is 1, so the rest must be 0. A seventh minus a sixth is negative 1 over 42. So I have to add n over 42. Now, 1 over 42 and negative 1 over 30 and 1 over 6, and before that there is negative 1 half and 1, are called the Bernoulli numbers. They appear in a lot of areas, but I love this one because it took me, I wasted like almost a year in my life working on this simple problem. Simple with Bernoulli numbers. Without them, I had no clue how to find. So once you tell me what the first term is, yeah, I'm going to multiply that by 7 over 2, by 8 over 3, by 9 over 4. It's no big deal. But how do I find these? These are the Bernoulli numbers. And how do you find them? It turns out that there is an equation that allows you to do that. I think I printed the Pascal triangle. Did I drop it? Because we will need, well, you don't really need it, but I am a fan of Bernoulli, I'm sorry, of Pascal triangle. And that's what I'm going to use here. How do we find these Bernoulli numbers that we are going to call them B? Some people refer to the first one, which is 1, as B sub 1, and others refer to it as B sub 0. So it really doesn't matter what you call it because you can arrange the equation to give you these. So I'm going to call it B sub 0. I'm going to say this is the generating number. B sub 0 is 1. Now I want to find B1, which is the negative 1 half, and then B2, B4, not after, I'm sorry, B4 with the sum of 4, B6, B8, B10, and so on and so forth. The odd ones equal 0, so we are not going to waste our time. Remember, I don't have a column here. I jump from n cubed to n. So there must be a 0 Bernoulli number here, a 0 Bernoulli number. And now it starts to make sense, right? There are zeros. But how do we get, say, B1? The equation is as follows. Because you are calculating B1, you always say negative 1 over, if I want B1, I divide by 2. When I try to find B2, I will divide by 3, and so on and so forth. Times the summation. What is the summation? I'm going to take, if I'm doing if I want B1, I'm going to take 2 take 0 times B0 plus 2 take 1 times B1, and these should add up. These should give me, I'm sorry, plus. No, I don't. Yeah, I don't. I do have that. Um, 2 take 0 is 1. B0 is 1. Yeah, I'm solving for B1, so why do I multiply by anything for B1? No, there is nothing. This would give me B1. This would give me B1. Okay, so 2 take 0 is 1, B0 is 1 times negative 1 half. You get B1 equals negative 1 half. If I want to get B2, I'm going to say it's negative 1 over 3 because this is 2. And then I multiply by the previous B's. Notice 3 take 0 times B0 plus 3 take 1 times B1. So what do I get? I get negative 1/3 times. This is 1 and this is 1. This is 3 and that's negative 1 half. So minus 3 halves. Negative times negative. Well, 1 minus 3 halves is negative 1 half. Negative 1 half times negative 1/3 is positive 1/6. I don't have a B3, right? B3 we said is 0. So B4 equals negative 1 over 4 times, where is, oh, here it is. 4 times 0, which is 1. 4 times 1 is 4. 4 times 2 is 6, right? But I'm sorry, I'm doing 5 because it's this is 1 over 5, and this is 5 take 0 B0 plus 5 take 1 B1 plus 5 take 2 B2 equals negative 1/5 times 1 times 1, negative 1 half. So this is negative 5 halves because 5 take 1 is 5. You see it here. 5 take 2 is 10. So plus 10 times this 1/6. So what is that? 1 minus 5 halves is negative 3 halves. Negative 3 halves, you can think of it as negative 9/6, right? 3 halves is negative 5/9/6 plus 10/6 is positive 1/6. 1/6 times negative 1/5 is negative 1 over 30. Negative 1 over 30. Then you do B6. It's negative 1 over 7 times 7 take 0 B0 plus 7 take 1 B1. After that, they are only, as you see, after B2, we go to B4. There is no B3. Plus 7 take 2 B2 plus 7 take 4 B4. Well, negative 1/7 times 1. Well, I didn't need the parentheses. Negative 1 half times 7 is negative 7 halves. 7, this is 21, right? 7, 21. So plus 21 over 6, that's B2. B2 is 1/6. Plus 7 take 4. 1, 2, 3, 4. So that's 35 times negative 1/30. 30th. Well, we can do some simplification. If I simplify by 5, I get 7 and 6. I divide by 3, I get 7 and 2. So you see that these two cancel. You get negative 7 half plus 7 halves are 0. 1, 1 minus 7, 6 is negative 1, 6. Negative 1, 6 times negative 1, 7th is positive 1/42, which is that. The next one is negative 5 over 66. They get very complicated sometimes. And it's really hard to get more than that. But of course, there are tables for the Bernoulli numbers that you can use to solve the sum of any power. Theoretically, any power you want, you can simply do that. You see that in S7, I'm going to multiply that by 7 over 2. So that becomes n squared over 12. And then by 8 over 3. And then so on and so forth. And then a new Bernoulli number, which is Bernoulli number 8 in the 8th power. I can use the same logic to find it. Okay? I know it's a little too complicated, but really it was fascinating. I spent this time and my head would explode from thinking and trying to find a way. But when I found the Bernoulli numbers, I heard about them and I found them, I said, how did this guy, hundreds of years ago, without calculators, without anything, he came up with, a way to generate these through integration. And it was mind-boggling. And it's one of the things I love about math, is that no matter how good you are at math, you will find there were geniuses living before you. And of course, we have geniuses with us living right now. And you wonder, how do these people get that talent? I wish you would be one of them one day. And I hope if I can help with a little bit, as much as I can. And I wish you all the best. Thank you very much for watching. Hope to see you soon. Bye.